So in the last video, I introduced De Morgan's law. One of the reasons why those laws are actually really useful is that they lead, they basically open the topic of all NAND transformation and all NOR transformations. I'm going to talk about what those things mean. Basically, we have been talking about all those gates, like the AND gate, the OR gate, the exclusive NOR gate, the NOR gate, and so on and so forth. But it's actually pretty complicated to make a circuit with all those gates all together, and it's not what they do on a large scale. So what they do instead is to choose only between making everything with NAND gates or with NOR gates. The reason for that is that it's actually way easier to handle a circuit which has all the gates with that are the same. And not fancy stuff like a mixture, a blend of exclusive NOR and OR and other things. So in this video, I'm basically going to talk about all NAND and all NOR transformation. So what's a NAND transformation? Well, a NAND transformation basically says two important properties. That x times y is equal to x, and we use this symbol here, y, with the arrow, not, and it says that x plus y is equal to x naught, y naught. While a NOR transformation basically says the opposite. So that x times y is x naught, then this one down, and then y naught. And it also says that x plus y is x down, with this arrow down, all with a naught. So we can do a transformation by knowing only those two things, which are basically derived from the De Morgan's law. So what do we do? Well, let's just try with an example, shall we? So what's the NAND transformation? Of the following expression? We have an expression which basically describes a circuit, and this expression is a function, so f of a, b, c, d, e equal to a naught times b plus c naught plus c times e naught times b plus d naught. Okay, so this is our expression, our function, and as you can see, we have both OR gates and AND gates, because we have a plus and a times. So if you remember what I was saying before, you have I have it here. that we can think about AND gates as times, so and multiplication, and OR gates as a plus and addition in binary. Right here, we can see that not only we have something that is not and so on, but we also have both of them, and we don't want them. We want everything to be NAND. So with this gate here, with single gate here. So what do? Well, it's a NAND transformation, so we know that we can use those two properties, okay? So what do? Well, we start by writing this down. And I can say, okay, fair enough. First of all, I'm gonna get rid of those things here inside the parentheses. So b plus c naught and b plus d naught. So since I have a plus and I'm in the NAND transformation, I can say that x plus y will be the same as not x, arrow upwards, not y. Okay, so I can say the same thing. So a naught is going to stay the same times. And now I'm going to say, okay, b plus c naught, okay, will be b naught and arrow upwards, and then c naught, naught. Then those things are going to stay the same. We have a plus, we have a c times e naught times, and now I'm going to get rid of this because it is going to be the same. So it's going to be like x plus y, so b plus d naught. So x plus y will be x naught, arrow upwards, y naught. So b naught, arrow upwards, d naught naught. Now, what do? Well, I'm going to rewrite again because I don't like to keep those two knots here, mostly because, you know, if you have, as I said before, if you have not 1 is 0 and not 0 is 1. But if you say not 1, it will be, you know, the same as saying 1. Because essentially not 1 will be, well, not 1, so 0 not 0, so 1. So whenever you have double not, you can simply rewrite them as the original value, so the original c and the original d. So we get a naught times b naught c without the double naught plus c times e naught times b naught and then just d. Right, so what do we do next? Well, the idea here is to get rid of this multiplication here, this product here, and this other product here. And to do so, I'm going to use this rule here. So x times y is like saying x, arrow upwards, y, everything with a naught. So we're going to do just that. So in this case, we would have a naught with the arrow upward, and then this thing, so b naught, upward c, everything with a naught, just like in here. Then we have a plus, we have c times, let's just do one thing at a time, e naught times b naught, or upward, d. Okay, now we're going to get rid of these other products, so this one here. So we have a naught, upward, b naught, or upward, c, everything with a naught, plus c times, which is going to stay, and now we're going to get rid of e times this. So we're going to do the same. So e times something is like saying this. So with the arrow upwards and everything with a not. So we will have E not with the arrow upward. Now we will have B not, arrow upward, D, everything with a not. We're getting closer because right now we only have these times here and then we add just the plus. So what do we do next? Well, we can actually get rid of these times here. So in order to get rid of this, we can do the same thing. So this one is going to stay the same. So A naught, arrow upward, B naught, arrow upward, C, everything with a naught, then plus C, and then we're going to get rid of this. So this becomes an arrow upward, of course, with E naught, arrow upward, with B naught, arrow upward, D. This one was with E like this, we was a not, and now we use this, and it was a time, so everything has to be with a not at the top. There we go. So now the only thing that is left is going to be this plus here, and we can get rid of this by using this property here instead. So x plus y will be x naught, arrow upward, y naught. So we have to, in order to put the arrow here, we have to put a not here and a not here. So it's gonna be pretty straightforward because it will be a naught, arrow upward, b naught, arrow upward, c, everything not. Then we have the arrow upward instead of the plus. So we're going to rewrite this and then we're going to say, okay, not one and not the other. So C with arrow upward, E not, arrow upward, B not, arrow upward, D. Everything is going to be with a not here and then a not here, just like before. But now we use this property, so we have to say with a not here on the first member and a not here in the second member. So now that we have a double not here, we can get rid of this. So we have a not with the arrow pointing upward, B not, arrow pointing upward, C. Then we have this one, we can get rid of this one as well. So with the arrow, then we have C, arrow upward again, E naught, and then we have this arrow upward, B naught, arrow upward, D, everything with a naught, and that's it, because those two cancel out, this one stays, and the individual one, of course, stay. So this one is our transformation with all NAND, which we can also write and rewrite as this: not A with the arrow upward, not B with the arrow upward, C with the arrow upward, C arrow upward, and then with a not, because all of this is going to be negated. So because it's going to be inverted when you have the output. So we have not, E with the arrow upward, not B with the arrow upward, D, and we close the parentheses after that. So this is going to be our final answer. So instead of using different types of gates, we actually got the exact same expression with the exact same circuit doing the exact same thing, only with NAND gates. And this is extremely useful, because, you know, by doing this, your circuit is gonna be, you know, way easier. It's gonna be way easier for you to handle what the circuit does. So, it's kind of worth it's kind of worth it doing this. So that's pretty much it. And I'm gonna talk about in the next video. I'm gonna introduce the NOR transformation, but it's gonna look pretty much the same. It's gonna be pretty much the same.